friends, welcome to VK lectures. Here we are going to discuss the linear algebra of mathematical methods of physics. Linear algebra. We can classify the matrices into two categories. Either it can be symmetric matrix or a skew symmetric matrix. Now what do you mean by symmetric matrix? If you have a matrix A and you take the transpose of that matrix, then if you are getting the same matrix A, then this is called A. Then A is said to be symmetric. Okay. Now how can you what is the form of the symmetric matrix? Here A, B, C, these are the diagonal elements, and D, E, F are the upper of diagonal elements, and the lower of diagonal elements should be as same as the upper of diagonal elements, that is D, E and F. Here D, E and F is there, the same should be repeated in this form D, E, F. So about the skew symmetric matrix, if you have a matrix A and you take the transpose of that matrix, and if you are arriving at a matrix which is the negative of the original matrix, then this is called skew symmetric matrix. Skew symmetric matrix. For a skew symmetric matrix, the matrix should be in this form. The diagonal elements should be 0 and the off diagonal elements, the upper off diagonal elements should be the negative of the lower off diagonal elements. Okay, now coming to the next point regarding the symmetric matrix, the number of independent elements in the matrix. Now let us count the number of independent elements: A, B, C, D, E and F. So there are 6 independent elements for a symmetric matrix of order 3. And how do you calculate this? This is n into n plus 1 by 2. Here n is the order of the matrix. So here the n is the 3. N is 3, that is the order is 3. 3 into n plus 1, 3 plus 1 by 2. So that is equal to 3 into 4 divided by 2, that's equal to 6. So we got 6 independent elements. Now coming to the skew symmetric matrix, the number of independent elements in the skew symmetric matrix is given by n into n minus 1 by 2, where n is the order. Here order is 3, 3 into 3 minus 1 by 2, that's equal to 3 into 2 by 2, that is equal to 3. So for a skew symmetric matrix, the number of independent element is given by n into n minus 1 by 2, while for symmetric matrix it is given by n into n plus 1 by 2. Orthogonal matrix. Another category of a matrix is orthogonal matrix. Let us just define an orthogonal matrix here. It will be of the form A, B, C, the diagonal elements, D, E, F, the off diagonal, and here also this will be similar to the symmetric matrix. Now what is the peculiarity of orthogonal matrix is A times A transpose is equal to I, where I is the identity matrix. Now we have already studied that if A into B equal to I, then B is nothing but A inverse. Now similarly, if you apply this particular idea into the first equation that we have here, then what we are going to get is A inverse equal to A transpose. Now for an orthogonal matrix, the inverse of the matrix is nothing but the transpose of the matrix. So if you are asked to find out the inverse of an orthogonal matrix, you have to just take the transpose of the matrix. Now for an orthogonal matrix, the determinant of the orthogonal matrix will be equal to 1. Now considering this as an orthogonal matrix, this is psi 1 and psi 2, this is the entire matrix, and this is the psi 2, the entire column. This is column 1 and this is column 2. So this would be a 2 by 2 matrix. Here you will have another element. Let me call it as psi 1 dash, or this is psi 2 dash. So you will have 4 elements. Then the psi 1 star psi 1, this is psi 1 star psi 1 is equal to 1. This is called normalization. And psi 2 star psi 1 equal to 1. This is also normalization. Okay. And what about if you have, this is nothing but the bra vector and this is the ket vector. This is bra vector, you represent like this, which is in the complex form, and you represent the ket vector in the real form, or it is the conjugate of complex. The bra is the complex conjugate of ket. Okay, so this is similar to our for example, if you consider psi 1 as a vector, psi 1 dot psi 1 is equal to 1. Just for example, x cap dot x cap equal to 1, and x cap dot y cap equal to 0. Now on the right hand side, here you have two different bases, psi 1 and psi 2. So here you have psi 1, this is psi 2. When you take psi 1 and psi 2, you get 0. Similarly, when you take psi 2 and psi 1, you again get 0. So this is what happens. This is similar to x cap dot y cap equal to 0. Here y cap dot x cap equal to 0. Now for an orthogonal matrix, if you consider a wave function, this is the column C1 as psi 1 and the column 2 as psi 2 and column 3 as psi 3, then this equation psi 1 star psi 1 will give you 1, while psi 1 star, either it can be psi 2, this will also will give you 0, and another equation that is psi 1 psi 3 also will be equal to 0. That means if you make a dot product of column 1 with 2 and 3, or 2 or 3, you will get 0, while with the same one you are going to get 1. Okay, now two points regarding the orthogonal matrix. All rotational matrices are orthogonal. All rotational matrices are orthogonal, and the rows and the columns of orthogonal matrix are orthonormalized. These two conditions This is normalization. This is orthogonal condition. Orthogonal means perpendicular. A dot B equal to 0 means, if A dot B equal to 0 means, we can write A and B are perpendicular. A perpendicular to B represent A dot B equal to 0. This is called orthogonal condition. Orthogonal condition. Now, just now we have seen, this is the same thing that we have seen here. If you have rows and the columns of orthogonal matrix are orthonormalized, orthogonal as well as normalized. A three-dimensional rotational matrix will be can be written in the form. So this is r, theta and phi. That means in spherical polar coordinates we can write down the values of r, theta and phi as sin theta cos phi, sin theta sin phi, cos theta cos phi, cos theta sin phi minus sin theta, and sin phi, cos phi and 0. Here you have minus sin phi into x, y and z. Now this is sin theta cos phi, sin theta sin phi and cos theta. If you want to get the theta, you just have to do dou r by dou theta. Differentiate this particular row with respect to theta. You will arrive at the second row. Now how will you get the third one? Third row is divide by sin theta and differentiate with respect to phi, divided by sin theta. So here it will go, sin theta will go, here also sin theta will go, and when you divide by sin theta you have to differentiate by phi. So cos phi will become minus sin phi, sin phi will become cos phi, and the last term is 0. So this is an three-dimensional rotational matrix. So if you consider this as a psi 1, psi 2 and psi 3, then as we have said, psi 1, psi 2 will be equal to 0 and psi 1 will be equal to 1. This is again one more term you can write. It can be psi 1, psi 3 or ij, where I not equal to j. If I equal to j, you are going to get 1. So few other examples of normalizing conditions are psi 2, psi 2, psi 3, psi 3. For others you will get another 4 more pairs where it satisfies the orthogonal condition. Orthogonal condition. For normalizing condition you will have, for 3 dimension you will have only 3 conditions. That is, this is normalization condition. So the rows and columns are orthonormalized. Hermitian and skew Hermitian matrix. What is Hermitian matrix is? It is the transpose of complex conjugate. Transpose of the complex conjugate of the matrix. Either the transpose of complex conjugate, or you can first do the conjugate, complex conjugate, and then take the transpose. A dagger is equal to A star, that is the complex conjugate, and the transpose, it is very equal to, you take the transpose and do the complex conjugate. This is very same. Now what do you mean by the Hermitian? Hermitian means if you take the transpose and the complex conjugate, that means if A dagger equal to A, then this is called Hermitian matrix. And for skew Hermitian matrix, A dagger equal to minus A. The minimum number of real elements in the skew Hermitian matrix is n, where n is the order of the matrix, and in Hermitian matrix all the diagonal elements must be real. That means the A, B and C must be real. It cannot be a complex number, and the eigenvalues of the Hermitian matrix are also real. Now coming to the skew Hermitian matrix, the minimum number of real elements, that means the minimum real elements required for making a skew Hermitian matrix is 0. That means there is no need of a real element to be present in a skew Hermitian matrix. Now the diagonal elements are either 0 or pure imaginary. All A, B and C are either equal to 0 or pure imaginary number. Pure imaginary number examples are minus I, 3I, I. These are the examples. That means it should not contain, it should not have a real part. It should not contain a real part. For example, 3 minus 2i. This cannot be the elements. The elements, or that means the diagonal element cannot be of this form, 3 minus 2i. If A and B, these are the matrix, these are symmetric matrix, then AB, that is the product of AB, is also symmetric if the A comma B commutator, that means if what is A comma B means, this is equal to AB minus BA. This is what I mean by commutator A comma B. The symbol represents the commutation symbol. So if AB minus BA equal to 0, then AB is symmetric. That means if you have a symmetric matrix A and B, AB is symmetric if A comma B equal to 0. So this is what is given in the first point. Now the second point, that if A is a square matrix of order n, it can be any order n, then A can be written as, that means the square matrix A can be written as, or written in terms of the transpose. A can be written in the form of A and A transpose in this way: A equal to half into A plus A transpose. Now this A plus A transpose gives us the symmetric part plus half into A minus A transpose. This gives us the skew symmetric part. So if you have a square matrix A, then A can be written as in the form of symmetric and skew symmetric matrix in this way. Okay, this is true for Hermitian also. Now if A and B are Hermitian matrix, which means A dagger equal to A and B dagger equal to B. Then AB is also Hermitian, that means AB whole dagger equal to AB. Now how do you write the AB whole dagger? AB whole dagger is equal to B dagger A dagger. It will get interchanged. So this is equal to AB only if A comma B equal to 0. A comma B equal to 0. Now B dagger, because we already know A and B are Hermitian, so this B dagger A dagger can be written as BA. Now BA equal to AB means AB minus BA equal to 0. If AB minus BA equal to 0, you can write A comma B commutator equal to 0, because we already have seen what is A comma B equal to AB minus BA. A comma B equal to 0 implies AB minus BA. So this is given by the third statement. If A and B are Hermitian, then the product AB is also Hermitian only if it is commutative. A comma B equal to 0 or A commutes with B. You can write it as A commutes with B. In other words, you write it as A and B are independent. Another class of the matrix is the unitary matrix. It is similar to orthogonal matrix. The peculiarity about the unitary matrix is this is consider A as a matrix, and A dagger is the Hermitian of the matrix A, and when you multiply matrix multiplication A on A dagger, you are getting I. Now so this is equal to A dagger A, which means the order of the multiplication is not important. Now as we have done earlier, A into B equal to I implies B is equal to A inverse. This I is the identity matrix. Then similarly, if you put this A into B equal to I here, this is A, this is B, and this is equal to I, which implies B equal to A dagger, that is A inverse is equal to A dagger. That is, for a unitary matrix, inverse of the matrix A is nothing but the A dagger, which is the Hermitian matrix of A. The determinant of the matrix is 1, unitary matrix is 1, and this determinant is nothing but the modulus of the determinant. Okay, now considering this as a matrix A and the three vectors, that is, this is psi1, psi2 and psi3. These are three columns of the Hermitian or the unitary matrix A. Then psi1 is equal to 1. This is the bra vector and this is the ket vector. Psi1 equal to 1 and psi1 psi2 equal to 0, and psi2 equal to 1 and psi2 psi1 equal to 0. This condition is called normalization condition, normalization, and this is orthogonal. Now with this concept we will understand 2 points here, that is the rows and the columns of unitary matrix are orthonormalized. The determinant of unitary matrix is unit modulus. That means if you have a matrix A which is unitary, this is if A is a unitary matrix, then A will have a determinant, either it will be +1, -1, minus plus I or minus I. Either of these 4 must be the determinant of the unitary matrix. You cannot have any other determinant. The determinant for a unitary matrix should be either of this. Properties of determinants. Properties of determinant. The first one is determinant of AB equal to determinant of A into determinant of B, and determinant of A transpose is equal to determinant of A. Determinant of K times A, where K is some constant, then this is equal to K power n into determinant of A, where n is the order of the matrix. Okay. For example, if this is the matrix A, I am multiplying this matrix by K, then determinant of Ka will be equal to K power, what is the order of the matrix? Order of the matrix is 3. This is K power 3 into determinant of A. Suppose if the determinant of A is equal to 2 and value of K equal to 2, then this is 2 power 3 into determinant of A, that is 2, that is equal to 2 power 3 is 8 into 16. So this will be your determinant for the matrix multiplied by the constant K. And the last point, determinant of AB will be equal to determinant of BA if both A and B have same order. That means A comma B should be of n, order n. Either it should be 2 by 2 or 3 by 3. Both A and B should be either 2 by 2 matrix or 3 by 3 matrix. It should be square matrix. Both the rows should be equal to column, right? When we have to multiply two matrices, the number of rows should be equal to number of columns. Number of rows for the matrix A should be equal to number of columns for the matrix B. But if determinant of A is equal to determinant of BA, this is possible only if A and B have the same order. More properties of determinant that we have learned in our earlier classes, that is, rows or columns are interchanged. If the rows or columns are interchanged, sign of the determinant changes. The sign of the determinant means if you have determinant A equal to +2, then after changing the row or column you get A dash. The determinant of A dash will be equal to -2. Okay. Now if any two rows or columns are same, then the determinant is 0. That means if there is any row elements or the column elements of a determinant are same, then the determinant is equal to 0. Determinant of a diagonal matrix. Now for example, you have a diagonal matrix here. Diagonal matrix means only diagonal elements will be there, all other elements are 0. In such cases, the determinant of this matrix will be equal to product of the diagonal elements. If we are writing it as A, B and C, it will be equal to ABC. Determinant equal to ABC. Now determinant of a triangular matrix. Triangular matrix means it can be either upper triangular matrix. For example, can be either this or this. That means only okay, so all other elements are 0. Okay, so this is called upper triangular matrix. This is lower triangular matrix. Determinant of a triangular matrix is the product of diagonal elements. Whatever is the diagonal elements here. An example of the triangular matrix I will give you. This is A, B, C, D, E, F. This is upper triangular matrix. All other elements are 0. So in this case, for example, this is A, and the determinant of A will be equal to ABC. Okay, so that is what is called triangular matrix. For a triangular matrix, determinant of A equal to ABC. Now determinant of skew symmetric matrix of order odd number. Now for example, if you have a skew symmetric matrix, now what do you mean by skew symmetric matrix? A transpose equal to minus A. Now if this A has an order either 3, 5, 7, then its determinant will be equal to 0. And if this skew symmetric matrix is of order 2, 4, 6, then determinant of this skew symmetric matrix is not equal to 0. That means only if the order is odd number, then the determinant equal to 0. Rank of a matrix. Now rank of a null matrix is 0. Now what is a null matrix? Null matrix means all the elements of this matrix A are 0. All the elements of this particular matrix are 0, then this is called a null matrix. Now the rank of the null matrix is 0. Now rank of A transpose equal to rank of A. The rank of A and A transpose must be equal to the same. Now rank of A plus B will be always less than or equal to rank of A plus rank of B. Rank of A plus B will be always less than rank of A plus rank of B. Now rank of a diagonal matrix. For example, now you have the diagonal matrix A, B, C. Now diagonal matrix means only diagonal elements will be present, all other elements will be equal to 0. Now rank of this diagonal matrix will be equal to number of non-zero elements. Number of non-zero elements in this matrix. For example, if A, B and C, A, B, C are not equal to 0, then rank equal to 3. Now if A equal to 0 and B, C not equal to 0, then rank equal to 2. if a comma b equal to 0 and c not equal to 0, then rank equal to 1. This is for the diagonal matrix. For a diagonal matrix, you just have to count the number of non-zero elements. Okay. Now for triangular matrix, the rank is equal to number of non-zero rows. Now here please remember, it is non-zero rows. Row should not be 0. Okay, you have to count the entire row which does not have zeros. Okay, now all rows are same or identical. For example, if you have a 3 by 3 matrix, if all rows are identical or equal, then rank is equal to 1. Then the rank of the matrix is 1 for if all the rows and columns, sorry, all the rows are same or identical, then it is equal to 1. Same means, for example, let us consider A, B, C. A, B, C. A, B, C. This is same. Identical means this is A, B, C. This is 2A, 2B, 2C. This is 3A, 3B, 3C. Okay, this is called identical. So in these two conditions, the rank is equal to 1. Eigenvalue of the matrix A. For a 2 by 2 matrix, you can calculate the eigenvalue lambda by lambda square minus trace of the matrix A into lambda plus determinant equal to 0. Now the trace of the matrix means the sum of the diagonal element. Trace means sum of diagonal element. Diagonal elements. Now in this case, trace is sum of A and D. Okay, now so this is trace is equal to A plus B. And what is determinant for this 2 by 2 matrix? Determinant is equal to AD minus BC. Now put this trace and determinant in this equation. So lambda square minus A plus B into lambda plus AD minus BC equal to 0. By this you are going to get an equation in a quadratic form, something like this: lambda square plus k lambda plus k dash equal to 0. Now by solving this quadratic equation, you can solve for lambda. You will get two values of lambda, either lambda 1 or lambda 2, because it is quadratic equation. Solution: you can either get the 2 lambda, lambda 1, lambda 2. This can be real. Then either lambda 1 can be equal to lambda 2, or you can get lambda 1 and lambda 2 as imaginary. All these are the possibilities. Now for a 3 by 3 matrix, the eigenvalue, you will get 3 eigenvalue: lambda 1, lambda 2 and lambda 3. These are the eigenvalues of the matrix. Now lambda 1 into lambda 2 into lambda 3, that is the product of the eigenvalue, is nothing but the determinant, and sum of the eigenvalues will be equal to trace. And what is this trace? A, B and C. So sum of eigenvalue equal to trace and the product of the eigenvalue equal to determinant. Eigenvectors. For 2 by 2 matrix, how can we find the eigenvectors? For example, we have got lambda 1 and lambda 2 as the eigenvalue. Corresponding to lambda 1, we will get the eigenvector psi 1, and corresponding to lambda 2, we will get the eigenvector psi 2. Now eigenvalues equal to lambda 1 lambda 2 and a psi equal to lambda psi. A times the eigenvector psi 1 equal to lambda 1 times psi. What is this eigenvalue? Eigenvalue is nothing but the mean value. Eigenvalue is the mean value or the average value. Mean or average value. Okay, so depending on this mean and average, we have got the vector, that is the eigenvector. Okay, so a psi 1 equal to lambda 1 psi 1. So after solving this, we will get wave function psi 1. Now for example, if this is a, this is the unknown quantity, that is our psi, equal to lambda times psi. Now by solving this equation, we will get ax plus by equal to lambda x and cx plus dy equal to lambda y. Now these two are the equations that we have got from the eigenvalue equation, and this is equations in two variable. Now what are the variables here? Variables are x and y. So there are two variables, x and y. There are two equations, so two equations and two variables. You can definitely find the values of x and y. So x and y, now this is x and y corresponding to psi 1 because we have considered lambda 1. Now similarly for lambda 2, you will get another set of equations which gives psi 2 as x comma y. Now either these equations can be used to get the psi 1 and psi 2, which are the eigenvectors corresponding to lambda 1 and lambda 2. For a 3 by 3 matrix, assume that lambda 1, lambda 2, lambda 3 are the eigenvalues and they are non-degenerate. Now what do you mean by non-degenerate? Lambda 1 not equal to lambda 2 not equal to lambda 3. Then the eigenvalue corresponding to lambda 1 can be found out by using a minus lambda 1 I equal to 0. This is the characteristic equation, and by solving this you will get psi 1 corresponding to lambda 1. Okay, now if you want to find out for psi 2, you have to use 2 instead of 1 in this characteristic equation, so you will get corresponding to lambda 2. Similarly, you can get for lambda 3, and all these values lambda psi 1, psi 2 and psi 3 will be distinct. Okay, and they does have distinct eigenvectors for non-degenerate eigenvalue. For a 3 by 3 matrix, the possible values of the eigenvalues are lambda 1, lambda 2 and lambda 3, because it is a 3 by 3 matrix. Now for non-degenerate lambda value, that means when lambda 1 not equal to lambda 2 not equal to lambda 3, which means no two eigenvalues are same, then we can find the eigenvector corresponding to lambda 1 by using the characteristic equation. So this is the characteristic equation. A minus lambda 1 times I equal to 0. By solving this equation, we will get the value of the eigenvector corresponding to lambda 1, that is psi 1. Similarly, if you put lambda 2 instead of lambda 1, you will get psi 2 and psi 3. Now the question is, if the eigenvalues are degenerate, for example lambda 1 and lambda 2 and lambda 2, that means eigenvalue, this is the first eigenvalue, second eigenvalue and the third eigenvalue. If the second and the third or any one of the any two of the three eigenvalues are same, then how we will find out the wave function or the wave vector, the eigenvector corresponding to lambda 1 and lambda 2. For lambda 1, we can use the same method as we have followed in the case of non-degenerate eigenvalue. For the lambda 2 and lambda 2, that is the second and the third eigenvalue, which is degenerate. Degenerate means they are same. Same means degeneracy equal to 2. This is also called algebraic multiplicity. Algebraic multiplicity. Okay. Now to find the rank, that means once you have the degenerate eigenvalue, your first step is to find the rank of the matrix A minus lambda I. This is one matrix. Together you have to find the rank. Okay. Now they have distinct eigenvectors if, now this is the concept, they have distinct eigenvectors, that means psi 1, psi 2, okay, this is psi 2 and psi 3. Psi 1 we will get it from here, right? Psi 1 we will get it from the non-degenerate eigenvalue, because psi 1 is, because lambda 1 is non-degenerate, lambda 2 and lambda 3 are degenerate, they are equal. So to find out psi 2 and psi 3, we want to know whether psi 2 equal to psi 3 or psi 2 not equal to psi 3. This is what we want to know. If n minus r equal to 1, that means n is the order of the matrix, r is the rank of the matrix. If n minus r equal to 1, they have same eigenvector, which means psi2 equal to psi3. Okay, if n minus r not equal to 1, they have different eigenvectors, that means psi2 not equal to psi3, and this n minus r is called geometric multiplicity. Geometric multiplicity. Fine. Properties of eigenvalues. Now suppose you have a matrix A given by A, B, C, D, E, F, G, H, I, and the corresponding eigenvalues are lambda 1, lambda 2 and lambda 3. Then the trace of the matrix A is given by A plus B plus C, which will be equal to lambda 1 plus lambda 2 plus lambda 3. So trace is equal to sum of the eigenvalues. Now determinant of the matrix A equal to lambda 1 into lambda 2 into lambda 3. Determinant of A is equal to product of the eigenvalues. Now eigenvalue of A transpose, for example, you find out by the transformation A transpose, then what are the eigenvalues? Eigenvalues will not change. It will remain lambda 1, lambda 2 and lambda 3. Now the eigenvalue of A power m. Suppose you are exponentially multiplying, you are finding out the eigenvalue of A power m. You are multiplying m times the matrix A, then your eigenvalue will change by lambda 1 power m, lambda 2 power m, lambda 3 power m. For example, if the eigenvalues of this matrix are 1, 2 and 3, and I wanted to find out the eigenvalue of A squared, then lambda will change to 1 square 1, 2 square 4 and 3 square 9. This is how the lambda value will change when you multiply the matrix with itself or any value of m. Okay, now lambda value for A inverse. For example, I find out the inverse of the matrix, that is A inverse, then how will you change the lambda? It will become lambda 1 power minus 1, lambda 2 power minus 1, lambda 3 power minus 1. That is 1 by lambda 1, 1 by lambda 2 and 1 by lambda 3. Now the eigenvalue of k power A, where k is some constant, that means I am multiplying this matrix A by some constant k, then what will happen to its eigenvalue? Eigenvalue will also get multiplied by k times. Okay, now if I am finding the adjoint of this matrix, adjoint of the matrix A, then how the lambda will change? Lambda 1, the first lambda will be equal to determinant of A by lambda 1, determinant of A by lambda 2, determinant of A by lambda 3. These are the eigenvalues of adjoint of A. This is the first eigenvalue, second, and this is the third. Eigenvalue of some special matrices. Now suppose if you have a matrix A equal to the elements A, B, B, A, B, B and A, then lambda 1 equal to A plus B, lambda 2 will be equal to A minus B. And suppose if you have a 3 by 3 matrix A, B, 0, B, A, 0 and 0, 0, C, then lambda 1 equal to A plus B, lambda 2 equal to A minus B, lambda 3 equal to C. Now suppose you have a matrix like this is 3 by 3 matrix A0A, 0A0 and A0A in row wise. So lambda 1 equal to 0, lambda 2 equal to A and lambda 3 equal to A. Now for example I am writing here 2 1 1 2, then lambda 1 equal to 3 and lambda 1 equal to lambda 2 equal to 1. Suppose I have the matrix 3 2 2 3 0 0 4 0 0. Now how will you find out the eigenvalues? Lambda 1, lambda 2 and lambda 3. Lambda 1 equal to A plus B. So this is A, this is B. Right, 2 plus 3 that is 5. Then lambda 2 equal to A minus B, that is A minus B, that is 1. And lambda 3 equal to C. So what is C? Here 4. Okay. So similarly if I write here 2 0 2 0 2 0 and 2 0 2, find out the lambda 1 equal to 0, lambda 2 equal to 2, lambda 3 equal to 2 times 2, that is 4. Now if the matrix A equal to 0 A 0 A 0 A 0 A 0, now lambda 1 equal to 0, lambda 2 equal to plus root 2 A and lambda 3 will be equal to minus root 2 A. Now this is another point. If the rows and columns are identical or same, if the rows and columns are identical or same, then the first eigenvalue will be equal to trace of A, trace of the matrix A. Lambda 2 will be equal to 0, lambda 3 equal to 0 and lambda 4 equal to 0. It continues for any n by n matrix. This is true. Now one example I can give you. So for example this is a 3 by 3 matrix 2 1 2 2 1 2 and 2 1 2. So this is rows and columns are identical, so here the rows are same. Then what is the lambda 1? Lambda 1 is equal to 2 plus 1 plus 2, that is 5. And what about lambda 2? It is equal to 0, and you will have one more lambda which is also equal to 0. Okay. Now for the skew symmetric matrix, this will be of the form 0 0 0, that is the diagonal elements must be 0. What do you mean by skew symmetric? A transpose equal to minus A, then the diagonal element must be 0 and the off diagonal element A, B, C will be correspondingly the minus of the off diagonal element in the lower part. Okay, now in this case what are the eigenvalues? Lambda 1 equal to 0, lambda 2 equal to plus root of a square plus b square plus c square, and lambda 3 equal to minus root of a square plus b square plus c square. If there is this is a note, if there is 1 in any, that means this is not 1, this is I, this is complex number. If there is one complex number in such a way that there is if there is one complex number in the eigenvalue, then there must be another eigenvalue which has minus I. For example, if I have a matrix A and corresponding lambdas are 2 and 1 plus I, then the lambda 3 should be equal to 1 minus I. If there is 1 plus I, there must be 1 minus I as the eigenvalue. For example, if there is 2I, there must be minus 2I. If there is 3 plus 2I in the eigenvalue, the another eigenvalue should be 3 minus 2I. This is true for all matrices. Okay. Diagonalization of a matrix. Now suppose you have a matrix A and S is a matrix. Now suppose let us take this A. You have A, B, C, D as the elements, and you can find out the eigenvalues lambda 1 comma lambda 2 with the help of the characteristic equations. Then the diagonal matrix is nothing but the lambda 1 and lambda 2 in the form we are writing the A in terms of lambda 1 and lambda 2, that is the eigenvalue. Now what is S? S is a matrix formed by the eigenvectors psi 1 and psi 2 if you are considering 2 dimension. If there is 3 dimension, there will be psi 1, psi 2 and psi 3. So S is a matrix formed by the eigenvector, and D is a matrix formed by the eigenvalues. Now S inverse, that is the inverse of the matrix S into A, that is the original matrix, into S will give us the diagonal matrix of A. Now this diagonal matrix D and the matrix original matrix A are called similar matrix. That is why S, it is S inverse AS. So A and D are similar matrix. Now A and D have same eigenvalues. They have the same eigenvalue. They have the same trace. Since they have same eigenvalue and trace, they will obviously have the same determinant. But the eigenvectors may or may not be same. It need not be same. It can be different eigenvectors. Now A and D are called similar matrix, and S is formed by the eigenvectors of A. Now let us see, for a 2 by 2 matrix and 3 by 3 matrix, how can we whether we can find the diagonalized matrix or not. Now for the case of 2 by 2 matrix, if the eigenvalues are distinct, that means lambda 1 not equal to lambda 2, then it is diagonalizable, and if lambda 1 equal to lambda 2, it is not diagonalizable. You cannot diagonalize a 2 by 2 matrix with same eigenvalues. For a 3 by 3 matrix, if lambda 1 equal to lambda 2 equal to lambda 3, that means distinct eigenvalues, then you can diagonalize. And if any one of the any two of the three eigenvalues are same, then you cannot, or you may or may not be diagonalizable. Either you can diagonalize, okay, or you cannot diagonalize. Both these are possible, but when all the eigenvalues are same, then you cannot diagonalize. Okay, now there is a question: how can you understand whether it is diagonalizable or not? For that, we need to find out the algebraic multiplicity or the degeneracy. Degeneracy is what is lambda 1 equal to lambda 2, right? So the degeneracy is 2. That means eigenvalue with maximum degeneracy. How many number of values have the same eigenvalue? That is the called degeneracy. Okay, if this algebraic multiplicity, we will represent it by D, or the degeneracy. If find out the D, then you need to find out the geometric multiplicity, which is n minus r, where n is the order of the matrix, r the rank of the matrix. Then find out D and n minus r. If the algebraic multiplicity is equal to geometric multiplicity, then A is diagonalizable. Okay, it is diagonalizable only when D equal to n minus r, algebraic multiplicity equal to geometric multiplicity. Now there is another point: if A and B are diagonalizable matrix, then A comma B equal to 0. That means commutator of A comma B equal to 0, which means AB equal to BA, or you can put it in the reverse order also. If A comma B equal to 0, that means the commutator of A comma B equal to 0, then A and B are diagonalizable. Here we have a 2 by 2 matrix A. If the roots are real and distinct, by roots we mean that the eigenvalues lambda 1 and lambda 2, since it is 2 by 2 matrix, we have two eigenvalues. If they are not equal, then e to the power at, where A is the matrix, is equal to 1 by lambda 1 minus lambda 2 into e to the power lambda 1 t into A minus lambda 2 into I minus e to the power lambda 2 t into A minus lambda 1 into I into lambda 1 I. Okay, now what is I? I is the identity matrix. Identity matrix, it should have the same order as A. And for the second one, if the roots are real and equal, that means lambda 1 equal to lambda 2, e to the power at equal to e to the power lambda t times I plus t e to the power lambda t into A minus lambda I. Now if the roots are complex, alpha plus I beta, then e to the power at equal to e to the power alpha t cos beta t plus 1 by beta into e to the power alpha t sine beta t into a minus lambda I. Here we are discussing the Cayley-Hamilton theorem. It says that for every square matrix satisfies its characteristic equation. Now by this we can find out the inverse of a e to the power a by changing a to lambda and a inverse to 1 by lambda. Okay. Now inverse of a 2 by 2 matrix A, B, C, D is given by 1 divided by AD minus BC into D minus B minus C and A. Okay. Now for a matrix A which is having the order n or n by n, this is an square matrix, determinant of e to the power a equal to e to the power trace of a. Determinant of e to the power a equal to e to the power trace of a. Now what is trace of e to the power a? Trace of e to the power a is e to the power lambda 1 plus e to the power lambda 2 plus e to the power lambda 3. Now here you have a 2 by 2 matrix which is A, then e to the power A is given by alpha naught I plus alpha 1 A. Now e to the power lambda is equal to alpha naught plus alpha 1 times lambda. For a 3 by 3 matrix, e to the power A equal to alpha naught I plus alpha 1 A plus alpha 2 A square. E to the power lambda is equal to alpha naught plus alpha 1 lambda and alpha 2 lambda square. This alpha naught, alpha 1 are constants. Lambda is the eigenvalue. Then we have the matrix A, and the I is equal to identity matrix.